Okay, hi everybody. So hopefully you took a minute just to do the adding of the rational expressions. Someone want to type in what answers do you get? What does the numerator end up becoming for the first one? Okay, that's right. It is 10x plus 29 for the first one. And would somebody type in what the numerator became for the second one? And that's right. It is 4x plus 41. You have that one of the more common errors in algebra is when you have a negative here, you distribute it through and it manifests itself eventually with a plus sign over there. So if you got 4x plus 29, that would be your error. There's a question about test 4. Yeah, you could turn it. We could have that due, the next day or the day after. Now we have completed parametric equations unit, which is really a big unit from this course, and we're starting this small algebraic thing, and then we get into something called matrices, which actually takes a few weeks, and then the course ends with one more topic, something called limits. But today's lesson is about what's called partial fraction decomposition, which is a algebraic technique that you need in calculus. Oh, wait, hold on 1 second. Okay, sorry about that. So decomposition is when you have a number that you want to split up into other numbers, like, integer like 5. There are many ways to split it up. More than one way, at least. You could use fractions if you want. Well, when you, depending on what you add together, so for the warm-up question, the things that we added together were 7 over x minus 2 and 3 over x plus 5. And their sum ended up becoming 10x plus 29 over x plus 2, x plus 5. So the question is, what if I were just given this thing? Are we able to split that up? So let's come over here. 10x plus 29 Oh, minus 2, thanks. Now, there are times in calculus where we're working with an expression like this, and this expression in this form is really hard to work with. Certain techniques from calculus don't work. So we want to be able to split it up into a sum where the pieces are simpler. And you might say, well, there's so many ways, just like there's so many ways to split up the number of 5 into something plus something else. But what if I told you that this was the sum of 2 fractions? What do you think some real useful, of all the ways to split this up, what do you think the denominators of those 2 fractions are likely to be? Good. So I see that it's likely that the denominators were x minus 2 and x plus 5. And I mean, the truth is there are an infinite number of ways to split up 10x plus 29 over x minus 2x plus 5. You could just take any fraction and subtract it from 10x plus 29, and get a really complicated answer. But the point of partial fraction decomposition is we want the two new fractions to be simpler than the original one and not like just as complicated as the original one. So we're going to make the assumption that like before the common denominator of x minus 2x plus 5 was created, these two things individually had denominators x minus 2 and x plus 5. So partial fraction decomposition will start with that like assumption. And we want to find the way of splitting up 10x plus 29 over x minus 2 times x plus 5 so that the denominators are x minus 2 and x plus 5. And we'll know that our technique worked if we end up with 7 and 3 for A and B. Now, there are two different methods of answering this question, and both of them are pretty quick. And I'm going to show you. You'll probably like the second method better, but I'm going to start by showing you method number 1. So I'll just put Roman numeral number 1. So method 1 is called the equating coefficients method. And the way it works, and this is the same thing you do with the second method also. Anyone have a theory about what step 1 might be? Just to throw it out there. What might the first step be in working out the values of A and B? Just curious if anyone has any thoughts on that. So maybe something with factoring. And I saw Yusef said multiply each side by x minus 2 times x plus 5. That's actually the right thing to do. So the first step, if I multiply the entire equation, both sides, by x minus 2 times x plus 5, the left side would become 10x plus 29. And the right side, when you multiply this term by x minus 2 times x plus 5, the x minus 2's would cancel out, and you would get a times x plus 5. And this term here, if I multiply that term by x plus 5 over x minus 2, the x plus 5's would cancel out, and the x minus 2 would be there. And that's actually the first step for this method and for method number 2. So I'll even come over here for method 2. It's also going to get 10x plus 29 equals a times x plus 5. Okay, that's going to be the first step for either of those. Now, method number 1 goes like this. We distribute the A through and the B through. And then we combine like terms. Well, there's A's and B's and X's. What I mean by like terms is the AX plus BX turns into A plus BX. So the terms that have X's in them get put together, and the terms that don't have X's in them, we just kind of write those. So method number 1 has this distributing and combining like terms. So I have an A, I have a B, I have X's. Anyone know what I do to complete this question? Jonathan says system. What system specifically? And I see Riley says yes. A plus B is 10, and 5 and 5a minus 2b is 29. That's right. See, this coefficient, the coefficient for two like polynomials to be equal, the coefficients have to be equal. So this thing becomes the 10, whereas the 29 becomes that. So that's our system of equations. So I'll come over here. A plus b is 10, and 5a minus 2b . And now the system of equations, I like to multiply both sides of this top equation by 2. Add the two equations together to eliminate the two b's. 7a equals 49. A equals 7. Come back to the a plus b equals 10. 7 plus b equals 10. A equals 3. And that is the answer. We can come back over here and change this to a 3, and that to a 7. And if you understand that, you've done your first partial fraction decomposition. Why don't I have you take a minute to do method number 1 with the other equation. Remember that one turns into 4x plus 41? So let's come over here and do 4x plus 41 over x minus 2, x plus 5 equals a times x minus 2 plus b over x plus 5. Go ahead, use method number 1 and take a minute or two to work out this one with method number 1. Go ahead and do that now. Okay, I'm going to put up the work here. You can see that the equation, the system of equations became a plus b equals 4 and 5a minus 2b equals 41, and a became 7 and b became negative 3, which is what we should have gotten because in the warm-up question we added 7 over x minus 2. Notice how b was negative because this was 7 over x minus 2 minus 3 over x plus 5. Okay, so any questions about method number 1 before I show you the other method? You'll like the other. Method 1 is fine. Anyone have any thoughts about some of the limitations of method number 1, like why it might get difficult for harder questions? What might be the issue with method number 1? Anyone have any theories on that they want to type into the chat? They could be fractional coefficients. If the denominator, both methods are going to actually use factoring the denominator, but that's true. That could be sometimes the partial fraction decomposition, when the denominator doesn't factor, you have to use like the quadratic formula. And yes, for Nicholas, if you have 3 terms, like an A, a B, and a C, because maybe there are 3 terms in the denominator, x minus 2, x plus 5, x plus something else, then there would be a C involved there. And your system would be 3 equations with 3 unknowns. And, well, systems of equations get pretty difficult once you're more than 2 equations, 2 unknowns. So we are going to get another method. And I will call this one method number 2. Okay, so, and you'll prefer to use method number 2. The only thing about method number 2 is that it's a little bit, there's going to be sort of a controversy about it. We'll see what that is in a second. Okay, here's how method number 2 works. So here you are, 10x plus 29 equals a times x plus 5 plus b times x minus 2. And remember, this came from okay, oh, let me not show you method number 2 yet. This came from multiplying both sides of the equation. Where did that happen? This came from multiplying both sides of the equation by x minus 2 times x plus 5. So this equation is going to be true if I put in a number. Like if I took this equation when it's finished with the 7 on top and the 3, and I stuck the number 3 in to both sides, well, I would get 59 in the numerator here, and I would get 8 as the denominator. I get 59 over 8. And if I put the same number 3 into both of these x's, I get 7 plus 3 over 8. And 7 plus 3 over 8, when I turn the 7 into 56 over 8, I would also get 59 over 8. So this thing is true no matter what x I put in. So that's also true about this. So if I put a number in for x, these 2 equations are going to be true. Well, you might say, oh, method number 2, number 2 is going to be called the convenient values method. Now, if you plug in a number, you could plug in any number you want. I mean, you could plug 3 in and get 59 equals 8a plus b. And you could plug in some other convenient value like 5 and get 79 equals 10a plus 3b. And you could do a system of equations, but that's not easier. That's still a system of equations. Now, the convenient values method says if it's true for any x value, and I see Jonathan had said, what if I put in the value x equals 2? let x equals 2. What's so convenient about putting 2 in as opposed to 3 or 5? Yes, Jonathan says it eliminates the b. Because when you put 2 in for x there, it becomes b times 0. So when you let x equals 2, you get 10 times 2 plus 29 equals a. This x also becomes 2 times 7 plus 0. Well, that's really convenient. So you get 49 equals 7a, and a equals 7. What about b? Anyone want to say into chat how you can almost like start this process over? Yes, if you let x equals -5, sort of go back to this and put -5 into all the x's, you would get -50 plus 29 equals 0 plus b times -7. So it would become -21 equals -7b, or b equals 3. And that is called the convenient values method. And in one sense, it's better. And Tamid has a good comment there. Are we allowed to stick in 7 and 3? Aren't those the very values that make this entire equation undefined? I will resolve that after. Because notice how this did get the right answers, 7 and 3. Okay, would you take a minute now to practice the convenient value method for 4x plus 41 over x minus 2, x plus 5. Okay, so take a minute to, even though we see there's a bit of a controversy about whether this second method, as easy as it is, whether it's actually mathematically legal to do. But assuming it is mathematically legal to use this second method, would you go ahead and use the second method? Okay, and you see on the screen that picking the convenient value of -5 for x, you might have done 2 first, doesn't matter which one you do first. Putting -5 in as the convenient value does get us b equals -3 really fast. And putting x equals, so when x equals 5, that works. But if you put in x equals 2, you get a equals 7. And those are the answers. It is 7 over x minus 2 minus 3 over x plus 5. And what we have here is enough that you'll need for to do the homework, and when we eventually have a test on it, and next year in calculus, if you know these two methods, there are times where the first method might be easier. There might be times, most of the time, the second method is easier. But there is a problem with the convenient values method, and Tommy pointed it out. It seems like, yeah, sure, you could plug in any value for x, and the left and right side will be the same, except those two values, because those are the two values. If you go back to the original equation, those are the values that make it undefined. So it seems like the only two values that are illegal are the actual only two values that we use. And I'm going to admit to you that for many years, I did not know why this was permissible. Oh, there was a comment there. Let's see. I think if you multiply the left and right by x minus 2, then putting in x plus 2 because they cancel. So it does have it. If you if you multiply both sides, you're saying that if you take the original equation and you just multiply both sides by x plus 2, just the x plus 2, is that what you're saying, Willis? You don't multiply by the entire thing? Let me think about that for a second. Let me come over here. So you're suggesting, because I'm hoping to find something easier than what I'm about to teach you about why the convenient values method is not illegal. Let's just take a look. X minus 2. So Willis says, what if instead I just multiply both sides by x minus 2? Then the left side becomes 4x plus 41 over x plus 5. And the right side becomes a plus b x plus 2. So Willis, here we are. So now what? Oh, I see. And now you plug in the x equals. Sorry, this should be a minus 2. Now when you plug in the 2, you get 49 over 7 equals a plus 0b over 7, and they cancel. Well, that works out pretty nicely. Sarah says, because you're not putting in the original equation, you put in the equation without the denominators. So Sarah, you're saying still it seems like a little bit like illegal to put 2 in. Is that, Sarah, what you're saying? Is that you're still not 100% convinced that this is legal? I will tell you, Willis, this is pretty good. I'm going to give you another thing that will. You're saying why it is legal? Yeah, this is pretty good because we're not plugging in. We're plugging in 2 into this equation and not into this one. But I could see some people still being a little bit uncomfortable with plugging 2 into any equation that started off like this. Seems like as soon as the question starts, it's like whatever you do, don't put in. So I'm going to give you another reason why. You don't really need to know why, but I'm going to do it mainly because I just learned it as part of one of my quarantine projects. I have this book from the 1700s, my favorite mathematician, Leonard Euler. I got this book about 12 years ago and never got around to reading it. His pre-calculus textbook that he wrote in the 1700s. And I started going through it, a couple of pages a day. And I found his explanation for why it's legal. So I'm excited because I just learned it. I'm going to show you what it is. Okay, let's go back to, here it comes. It's actually pretty complicated. Willis, your method might be convincing it definitely is better than having, when I didn't have any sort of explanation. But I'm going to give you a method that will satisfy all the doubters. Okay, about why is it legal to. So let me just get my mind straight on this. Let's say I were to subtract the minus a over x minus 2 from both sides. And then I were to combine this with a common denominator of x minus 2, x plus 5. Minus a times x plus 5. Now look at these two fractions. If these two the only way these two fractions can be equal to each other is if this one on the left, or the one on the right, is like a reduced version of the one on the left. It's kind of like I divided both sides by x minus 2 to like reduce this left side to become the right side. So what that means, I'm going to, so when I reduce this fraction, it turns into this one. And that means that this numerator divided by x minus 2 must equal the b. But for that to happen, we would say that x minus 2 must be a factor of this thing. Okay, because again, here's the x minus 5, that's this. So this divided by this must give me b. But that can only happen if x minus 2 is a factor of this thing. So I'm going to write down what we have. I'm going to write down x minus 2 is a factor of 10x minus 29 minus a times x plus 5. I'll say x minus 2 is, I'm going to say must be a factor of 10x plus 29 minus a times, what was it? Was it x plus 5? Now, what is the factor theorem? That's something from Algebra 2. What does the factor theorem say in general? If x minus a is a factor of p of x, what conclusion can you make? Yes, not only, you're right, the remainder is 0 when you divide. What else is 0? Yes, and p of a equals the remainder. So put those two things together. Riley says the remainder is 0. Willis says p of a equals the remainder. Put it all together. Equals 0. Thank you. That's the factor theorem. If x minus a is a factor, then p of a equals 0. So if I come back over here, so if x minus 2 is a factor of 10x plus 29 minus a plus 5, then I'll call that p of x if you don't mind. Then if I put in 2 for x, the answer has to become 0. And this becomes 49 minus 7a equals 0, or a equals 7. So I'm excited about that because I got this book about 12 years ago as a present, Euler's Analysis of the Infinite, Volume 1. it was a really expensive book. It was over $100, and I had it on my shelf for 12 years. And I took this opportunity, this quarantine opportunity, to like read. The idea is to read like 2 or 3 pages a day and see if I could learn some new stuff about pre-calculus that I've been teaching for all these years. So that's what I learned, and now you know it also. And that avoids, I feel like that avoids the issues, although you might have not been bothered by the original convenient values method. Okay, so now pick a method, whether you want to use convenient values method or the equating the coefficients method, and go ahead and do the partial fraction decomposition for this, and then we'll be done for today. So you can start working on that. You can chat about it. You can, which method is better? What are like the cool kids? Which method did they use? Which one's easier? Which one's more fun? Go ahead, work on this final question. Which method are people choosing to use? Okay, you could type in what did you get for the two numerators. And Chelsea says 4 and 2. And we will see that whether you used the equating coefficients method or whether you used the convenient values method, you got 4 and 2. This lesson, there was no, I didn't make a short video for it. I actually need to make one. So I'm going to have to make one so that otherwise people have to watch it just from the longer video. Let me stop the recording. See everybody. Well, I'm going to keep talking afterwards, but just for the recording part, recording is stopping now.